I have actually a quick question about the brackets in step four
Yes.
of converting to CNF. Do the brackets really matter? Because I believe in example one we didn't do them in the answer.
Here?
Do you get points deducted if you don't do the brackets? Because in
Um,
example we did it, but in this example we didn't.
you mean for this one or?
The example one, but in
Okay.
the step four of the
Oh, like
little,
these brackets or
yes,
these here?
yeah, we left them out in the last step, but um,
Um,
in
yes,
the yeah,
because these are two separate clauses. So it's as if you would write something like this. That is not really necessary, right? So that's
okay,
why you can omit them because they're just this is just one clause in itself.
okay.
So it's
But
just
why
separate.
did we add them in step four of the little on the right above in the
Here?
little, yeah, yes, okay.
Oh yeah. I mean, I guess they add them here, but in the end, if you write clause normal form, then you just have like the whole thing in DPLL. You would then have like four clauses in the end, and then you could just write them down like this. You have not P, not Q. In the second example, the brackets were left. Oh, you're right. Well, I don't think it matters that much, the brackets.
Okay,
I
okay,
don't
great.
really, I don't think you will get points deducted. I can check how I answered one of my questions last year. No, I personally did not use them. So
Okay,
that's,
so I can just leave them out in the end.
yeah. I think if they are separate clauses, then it's okay. Yeah.
Okay, great, thanks.
Yes, no problem. Yeah, personally, when I like Google some examples of just clauses itself, I see that like if it is needed, so when you have something like conjunction in between or a negation somewhere, then they have brackets, but otherwise they're just written down as just the thing itself. So maybe clause normal form. Yeah, this is the only kind of image I can find on it right now. I can just share it in the group chat. So you can see like if you have negation outside of brackets, you still have it. But if you then rewrite it to clause normal form, you don't have any brackets anymore. It's just the thing by itself. Cannot really find any other good examples, but no, not really. But you will definitely not get points deducted. It's just as if you would have a mathematical formula, right? And you would have 3 times 4, or you would write 3 times 4. Like you just add brackets, so it doesn't really make a difference to the meaning. That's what I was looking for. It doesn't really make a difference to the meaning in the end. Okay, so it's 10:30. Oh, the next slide, this one? Yes, okay, let me know when you're ready. Yes, okay. So now let's move on to DPLL. So DPLL is an algorithm for checking satisfiability. So if you remember what satisfiable is, there's at least one model for our formula, remember? Okay, so that is what DPLL can check for us. So in order to use DPLL, we have a little step guide. So first you write down the formulas you have, then you convert it to CNF. As you can see, this is just one step in the DPLL process, and there you have your little step guide, right, for CNF. Then you choose a variable, it could be alphabetically, and you set them to be false or true. And then you have to come to the conclusion if it's satisfiable or unsatisfiable. So for step 3, if there are no unit clauses or pure clauses, then you just choose alphabetically. But if there are, then you choose that one. So what is a unit clause? A unit clause is a single literal. So if we have, let's say, like 4 clauses, and one of them is just P, then we will choose P to be true. And then we move on with that. And a pure clause if a variable only occurs positively or only negatively. So what if we have like that? It's just an example. You can see that P is always positive here. So then you also choose P is true. When would you say variables? Do you mean the clauses that we just found with CNF? No, I mean like a single literal actually. So only P. So not this entire thing, but only P or only Q. Yes. Okay. So let's just try our hand at the first one. I'll just go with it. I'll just go through it. Can it be not P or just P? It can also be like that. Yeah. That is also a unit clause. So just if it is on its own. And it can also be negation of P, yes. Such as P or not P. That doesn't really matter. So I have 3 recap questions in the end, but would you guys just like me to go through this one and show you how you should do it? And then for the other 2, we try it together. Yes, okay, since it's quite new, right? Might be a bit intimidating, but don't worry, we're just gonna follow the steps. So here we have our knowledge base, which includes 2 formulas. This is one of them, and note the comma here. This is the second one. And they want you to prove or disprove whether the knowledge base is satisfiable using DPLL. Okay, so we just go back to our step guide. The first step is write down the formulas that we have. So this is our first formula. P or Q. Oh, I guess they're capital letters. P or Q. And, oh no. Can I please keep writing? Yes, please. Okay. Sometimes it just disconnects. We have Q implies R, and we have R implies not P. Okay, and then our second formula is not P with a by implication not Q. That's our first step. Then we want to convert it to CNF. So for this one, it's pretty easy, right? What do we do here? For CNF, we only have these conjunctions that we can split up. So if we want to convert it to CNF, all we get are 3 separate clauses. So we have P or Q, we get Q implies R, and we get R implies not P. And now we can also rewrite the implications to become not Q or R and not R or P. So far we're just applying CNF. If we do the same for the second one, do you remember what we do with by implication? If we have A by implication B, then we rewrite it so we have A implies B and B implies A. Like that. So if we would rewrite it, what do we get? We get not B implies not Q and not Q implies P. Right? I'm just having both implications here. Now this one is a little tricky. Let's see. We then use the negation, right? Oh no, sorry, the implication is first. So if we go to our CNF step guide, we remove implications. So here we just keep this as it was, and we have not P or not Q, and we get Q or P. Yes. Okay. Then we apply this negation to what is inside of here. So we get not, and then this entire thing, or flips around, not Q or P. So then again, we move the negations inward. So we get P and Q. This one stays the same, and we get not Q and not P. Yes. Okay, so what do we do next? We remove the conjunctions outward, right? So we would get P or not Q and P or not P and Q or not Q and Q or not P. In our case here, we can get rid of these two, because even if you have the value to true or false, it will always yield true. So we can just get rid of those. And then our two final clauses here would be P or not Q. And we would get Q or not P. Okay, so I went through it pretty quickly, but I'm just applying CNF here. Do you have a question about this step here? Why I did this or something else? Okay, so this here we had P or not P, and we had Q or not Q. So the entire thing about DPLL is then you choose literal and set it to be false or true. If we choose P is true here, this will yield true, right? So then we could get rid of it in DPLL. If we choose P is false, then we also get P is true. So it doesn't matter what we choose for P, this will always yield true. And when constructing DPLL, if something is a true variable, then you will not consider it anymore. So you will see that when I move on, if something is true, then you will kind of remove it from your clauses. So in our case, it doesn't matter whatever we choose for P or Q, this will always be true. How do I get to these clauses in the first place? I applied this one, third step. So instead of having just R on the left-hand side, I had this entire formula on one side, or I had that one. So I did P times not Q, P times not P, Q times not Q, to Q times not P. So if you could refer to like math, you do that one times this one, that one times that one, that one times this one, that one times that one. Okay, I guess that one makes sense. And then we have another question. I don't understand why we swap the and or again. So the and or swapping only happens when we use negation. Yes, so someone's already implying it. When you have a negation and you move it inward, it swaps, okay? So with negation. So if you look back, here we had a negation outside, and we applied it to this entire thing. So not P becomes P, and not Q becomes Q, and this or becomes an and. Same for this other side. Not Q becomes not Q, not P becomes not P, and instead of or, we flip it so it is and. Okay, so every time you're multiplying times -1, as you said, you swap this one. The part after that, that is this one. So you have the or is kind of the multiplier in this case. So you do r times p with the or, and you do r times q with the or. So we do the same here. We do p times not q, so it becomes p or not q. And p or p, and q or not q, and q or not p. Okay, so keep your little CNF step guide with you. So we can write down our final clauses now. We also have it for the other one. We have p or not q, and we have q or not p. Okay, so what is our next step? We choose a variable and set it to be truth or false. We first have to check, is there a unit clause or a pure clause? Well, let's see. Does anyone see a unit clause or a pure clause here? Oh, okay, yeah. That's because of the and. For the other equation, how did you get number 3? That is just r implies not p. And because of this implication, we can rewrite it to not r or not p. Was that your question, Roberto? Okay, no, it's not more complicated. It was just that, yes. Okay, so now we move on. There are no unit clauses and there are no pure clauses, right? Because a unit clause is just a single literal, and the pure clause, if we see like only positive q or only positive p or only positive r, well, that's nowhere. So what do? We just choose. Let's set p to be false in our case. Oh, I feel like I need another slide maybe. Okay, so I have p is false. So what do we get for our clauses? Oh, I was trying to write on my computer. We have false for q. We have not q or r, that stays the same. We have not r or true. We have false or not q. And we have q or not p. So what happens to this first one? We can get rid of false because that doesn't tell us anything. So this becomes q. This stays the same. This one is true. Remember, we got rid of it here. So that's actually what you do. You just get rid of it. So we don't consider that one anymore. So we have a third clause now, which is not q. And we have a fourth clause, which stays the same. Isn't 5q or true? Oh, yeah, you're right. Excuse me. You are correct. So this is q or not true. So what do? We get rid of it. So these are the 3 clauses we end up with. So what do we do now? We see we have q and we have not q. So if we choose q to be true, sorry, let's just choose r to be true first. So we are left with the clauses q and not q. So can we ever get to a conclusion where everything is true here? No, right? Because if we set q to be true, then we get true and false. If we set q to be false, okay. Yes, we ignore 3 and 5 because they have a truth value already. That is true. Exactly. Oh, okay, then you understand. Okay, great. I thought it was about this part. So we're ending up with these 2 clauses. So this is a contradiction because if we choose q to be true, then one of them will be false. And if we choose q to be false, then one of them will still be false, right? So we cannot get an instance where both of them will be true. So what do we get here? We have to come to the conclusion if it's satisfiable or unsatisfiable. So in our case, we end up with a contradiction, which means we can never yield to a truth value and that means it will be unsatisfiable. What if P and Q are true? What if P and Q are true? Okay, let's try it with P is true. Okay, we can do that as well. I'm going to insert an extra slide here because I didn't know I needed this much space. Let me see, maybe I can just copy it, but then I kind of want to get rid of this part. Okay, wait. Okay, so we got a contradiction for the last one, right? So now let's try it with P is true instead. Oh my goodness. Can you please work? Hello? I think my laptop is crashing. Can you guys still hear me?
Yep.
Yes? Okay. I feel like my laptop is not responding. Oh dear. Can you also see me still?
Yep.
Okay. My screen is frozen. I'm not really sure what to do right now. I'm just gonna going to shut down PowerPoint and then restart it again, okay? I'm sorry, guys. I think my laptop couldn't handle the fact that I'm doing Zoom and the tablet and PowerPoint. Oh, I got rid of my notes. No. Okay, I will share my slides with you once I did the other group, okay? So then I'll hopefully will have my notes there. But we just did DPLL for this one. I'm so sorry, guys. I really could not prevent this. Okay, so let me just write down very quickly what our clauses were. So we had P or Q, not Q or R, not R or not P, P or not Q, and Q or not P. Okay, I also have written notes of this. I can also send you a photo of that, so don't worry. Okay, so we just did P is false and Q is true or false. We had a contradiction in the end, right? So let's now try P is true, right? That was a suggestion in the chat. Let's try P is true. If you go to the file and do it, okay, that is a good, I'll just make a photo of that. But after you guys, I have another group, which I will like write down everything as well. So if that one saves correctly, I hope it will. I'll just add an extra slide to this one so I have enough space. Then I will send those to you guys. Is that okay? All right, so we have for P is true, we would get true for the first one. We would get not Q or R. We have not R or false, true, and Q or false. So what do we have left over? We get not Q or R, not R, and Q. Okay? Then we are kind of left in the same situation, right? Because now we can choose Q to be true. And what are we left with? We are left with R and not R. So again, we have a contradiction, right? Because this can never be true. What happens when we have a contradiction? What happens when it's not true? It's unsatisfiable. Okay, so for both P is true and P is false, so we tried every possible combination, right? For DPLL, we chose any variable, we set them to be true or false, and then we want to come to the conclusion, is this satisfiable? So we get true or unsatisfiable. We're not able to yield true in the end. Yeah, so you just pick the first variable to be true or false. You check, okay, what do I get in the end? And then you do the same with the other one. Exactly. Now we have a contradiction for both of them, because for the other one, we ended up with Q and not Q, so we cannot yield true out of this one. Here we also cannot yield true, so it doesn't matter what you choose for P, you will never get to true. So that is why it's unsatisfiable. Okay, please let me know if there are any questions. I know this might be a bit overwhelming, but we just have to follow this step guide, okay? So you write. Oh, sorry.
Sorry, I wanted to ask, during the exam when we have to write DPLL, should we write fast for P being false and then for P being true to show that we tried every option, right?
Yes, so for DPLL, this is the open question. You basically have to write down everything I just wrote down.
Okay,
so you have to start with the formulas, write them to CNF. So I basically always just started with writing it out. And then for my first step, I said, these are the clauses in clause normal form. I wrote them down. Then I said, there are no unit clauses or pure clauses. We choose P to be false. Then I said what yielded out of that one. Then I said we have a contradiction. We cannot continue. So now we choose B to be true. And then etc. Okay, someone said, I don't understand any of it. I got very lost, not really a specific question, but I don't understand how we get 1 to 5. Okay. I get that it is a bit overwhelming. Would you maybe like to try the other one with me? So then we can like do it together. I wouldn't be able to do it. Well, I mean, that way you're practicing, right? Okay, I'm gonna ask someone else then. But now let's move on to DPLL, the rest. Okay, so again, DPL is an algorithm for checking satisfiability. Also, is there anyone else that has any questions or uncertainties about this? Okay, let's just try another example. So DPL checks satisfiability, which is the opposite of entailment. So what does this mean? Let's see. What does this mean? It means that when we are at our final value and we know that it is satisfiable, then we can also say that it is not entailed, because it's the opposite, right? Similarly, we can say that when it's unsatisfiable, that it is entailed. So these are the same thing. So with satisfiability, with DPLL, you check satisfiability. If it's satisfied, then it is not entailed. If it's unsatisfied, then it is entailed. Okay, so remember that one. So how do we check entailment? You can do this by proof by refutation. So you have to prove entailment again. We saw this, you can do this with a truth table, remember? A sentence is entailed by a knowledge base if and only if it is true in all models of the knowledge base. So how do we do this with DPLL when it shows you the opposite of entailment? We take the negation of A and then we do the exact same thing we just did. That way we can check if it is entailed. We take our formula alpha, and if and only if the negation of alpha is unsatisfiable with the knowledge base, then we can say it is entailed. Okay, so this is an extra step. I'm so sorry, there's an extra step. DPLL by refutation. So you have your knowledge base and you have your formula. And if you want to check, we do this exact same thing, but now we just have an alpha and we just take the negation of that and we apply the exact same thing. Can you explain that with different words? Which part? The entailment? Yeah, okay. So you saw here, right? We knew what satisfiability was. Remember? Yes, okay. So satisfiability, if there's at least one model for our formula. The thing is, satisfiability is the opposite of entailment. So when is something entailed? It is entailed if A holds for all models of the knowledge base. So in our case with DPLL, because it checks entailment, or sorry, because it checks satisfiability, we can say when we come to the conclusion that something is unsatisfiable, then it is entailed because it is the opposite. If we come to the conclusion that it is satisfiable, then it is not entailed. Okay, so you basically just take the opposite. So every time you're DPLL and you come to the conclusion that it was satisfiable, then you can immediately say, okay, not entailed. Similarly, if it's unsatisfiable, you can immediately say the formula is entailed by the knowledge base. Okay, then how do we prove this with DPLL? We can do this by proof by refutation. So you take the negation of alpha and you solve it in the exact same way we just did. When you see that it is unsatisfiable, remember, then you can say it is entailed. The definition, I don't understand how it is written with the knowledge base. Okay, so if you look at this example here, a knowledge base is basically a collection of formulas separated by commas, right? So if you would do this with a truth table, it would take quite some time because you would have to like have every single one of them. So DPLL also does this, and this is our formula. Does that make more sense? Our knowledge base, which is written in these curly brackets, is a collection of formulas, and alpha is just a single formula that we have. Okay. All right, so if we want to do DPLL by refutation, is there anyone that wants to do this with me? I promise this one, the last one had quite a difficult one with the CNF. This one is way shorter. So because some of you were not responding, okay, Anna, do you want to do it with me?
Yeah, I can. Can you just go back to the last slide for a second because I didn't manage to.
Oh yeah, this one?
Yeah.
Yes, okay.
You just give me a second and.
Yeah, of course. Yes. So this is definitely like one of the hardest parts, and it is the open question. So I'm sorry about that. But just follow the step guide. If you know what CNF is, if you know what entailment means, so in our case, like set is not entailed, unset is entailed, and you need to know how to apply the truth and false values, that's actually all you need to do.
Okay, I'm ready. We can
Okay.
try. I'm not sure how this is gonna go, but we can try.
It's okay. There's one more question. What about it is the open question, like explaining how it works or solving a problem? You would get something like this. So you would get a knowledge base and alpha, and what we are going to write down right now, what I'm going to solve with Anna, that is all you have to write down. So you have to write down all the steps you take. Yes, I'm sorry. Sad face. Let's just try it together. So what was the first step of DPLL? We write down the formulas, right? So for the knowledge base, which formulas do we have?
So we have 3, right?
Mm-hmm.
We have not P or R.
Yes.
We have Q or not R.
Mm-hmm.
And we have not Q.
Yes. Can we construct these into closed normal form, or are they already done?
I think they're all already done, right? Because they're just single formulas. There's nothing.
Yes, exactly. So we don't have to construct these into closed normal form.
And
Okay.
we have the single thingy.
Yeah, so what do we do with alpha? We take the negation of alpha.
Yeah.
And then again, we convert it to CNF. So what do we do? What is the negation of alpha?
Not P and Q.
Mm-hmm. That is the normal formula, right? But if you want to take the negation, we negate this entire thing.
Yes.
Okay, so if we would write this into closed normal form, what do we get?
So we have to kind of multiply it by the minus and change the sign, right?
Yes, exactly. So what do we
You
get?
will have P or not Q.
Perfect. Okay. So we have 4 clauses in the end, which are these 3 and P or not Q. So let's just write them down. We have not P or R. We have Q or not R. We have not Q. And we have P or not Q. Is everyone in the chat following what we just did? So we took the negation of alpha, and we took our formulas from the knowledge base, and we converted them to closed normal form. So these are our final clauses. I don't understand the fourth. Okay. So the fourth is just the negation. Remember, when you negate something, you multiply it by the negation. So this becomes not P and this becomes not Q, and you flip the sign. But why are we negating it? Because we need to apply closed normal form to it. So one of the steps in closed normal form was to remove the negations inward, remember? So we do that here, here, by moving the negation inward. Oh, never mind. Okay, great. Do we convert the formulas in the knowledge base? In this case, we did not because it was already converted. Exactly. If you would apply all the steps of closed normal form to this, you find out that they are already in closed normal form. So we don't have to do anything to them. Okay, so these are the clauses that we have right now. I think this is clear. Now the next step is to choose a variable and set them to be false or true. And to do that,
we the unit clause, right? So it's
exactly
going to be easier.
So Q, not Q is our unit clause. So what do we choose for the value of Q?
Does it matter that much?
Sorry, the tablet is connected once again. The easiest thing is to choose a value that will yield a true value, right? Because then we know. Yeah. Okay, so what do we choose for Q?
So then we can choose false for Q, so not Q will be true.
Yes, so we choose Q is false and not Q will be true. So what happens to the first formula? Nothing, right? Because it does not include Q. What happens to the second formula?
The second formula will be false or not R.
Mm-hmm. The third one will become true, right? So we can get rid of it afterwards. And the fourth one
will be P or true. So
okay.
We can also get rid of it, right?
Yes, so we can rewrite this. So we have our first formula, P or R. And for the second one, we have only not R because this is already false. So we know that one will not yield us anything. So we're left with this. So what do we do now?
We can set P to true and we will be left with R or and not R.
Oh, sorry, I forgot the negation here.
Oh, so, yes, we can see
yes.
P to false. Yeah, I also
yes, exactly. So then we get true or R and we get not R. So what does that give us in the end?
That gives us R and not R.
Yes.
So that means that we proved that the negation of the alpha is unsatisfiable. So
Exactly.
we proved the thing we were supposed to prove.
Exactly. So if a contradiction again, right, this can never yield true. So as you said correctly, we say it is unsatisfiable. So is it then entailed or is it not entailed?
Then it is entailed, right?
Yes.
We were
Great.
supposed to prove that the negation is unsatisfiable, which we did.
Great.
Which means it is.
Perfect. You
Yeah.
did it. Great. Let's see. How did you know they were already in CNF? If you don't know, you just go through the steps, see if you can apply any of them. If you cannot apply any of them, then it's in CNF. Why do we take out the F when we get the next set of formulas? That's a good question, because if we have F or not R, and we want to know, right, if it can yield true, we cannot adapt this variable anymore. It is already set to false. So this is just the same as saying, I want to know whether this can yield true. Does that make sense? You cannot change that variable anymore. Yes. Okay, so the way that Anne did it was perfect. This is our answer. So why is satisfied not entailed and unsaid entailed? It is because DPLL checks for satisfiability. And the only thing that really adds to that, satisfiability is the opposite of entailment. So that is literally just why it is how it is. So we need to find, is it satisfiable, yes or no? When is it satisfiable? When there's at least one model that yields true. So can we find a model? Can we find something where if we set these variables to any value that we will yield true in every single instance? No, we cannot. So that is why it is unsatisfiable. And because unsatisfiability is the opposite of entailment, we say it is entailed. How do you draw that conclusion? I don't understand how to interpret the results with R. Yeah, exactly. So we have R and not R, and there's no way we can yield true out of this, because if we set R to true, then one of them is false. If we set R to false, then one of them is still false. So there's a contradiction, right? We can never get a true value. So if it was R and R, it would be satisfiable and not entailed. Exactly, if it would be like that. Yes, I think you get it. I think there was another question. True or R is R, isn't one true then? The answer I got was not correct. Exactly, so it is not entailed. So we can choose R to be false, which means we get true for everything, right? So true is then our final value. So then it is satisfiable. And not entailed. Thank you very much for pointing that out. Yes, I think I prepared like 4 other DPLL questions, but this was the one that I got from somewhere else. Let's see, so we can get P is false, we get true or R. So it is actually satisfiable and then not entailed. What if you find one variable that's satisfiable? Do you then have to go through all the other variables to see if something else is unsatisfiable? No, because you just have to find one model, right? So if our model now is Q is false, P is false, and R is true, this is a model, right? So then remember, satisfiable, we need at least one model, so you don't have to go back. We just know now there's at least one model, so it is satisfiable and thus not entailed. Okay. It is usually
So in this,
convenient to set everything to false when checking. Oh, sorry. I mean, it really depends. If you have a unit clause, then you check, okay, what will yield it to true? That's usually how I would do it. Why did you use T instead of R? Well, it would be T or R, right? So then it just yields to true. So this entire formula then yields to true. So we're only left with not R. So we can rewrite this entire thing. Okay, sorry. I think Kevin had a question. Yeah.
yeah. So in this case, you would say the knowledge base is satisfiable, and that means that the knowledge base is not entailed by alpha.
Yeah, so we say a sentence A is entailed or not entailed by the knowledge base, indeed. So in our case, we say sentence alpha is not entailed by the knowledge base.
Okay, yeah.
Yes. Okay, so we are spending more time on this than I thought, which is okay because it's very hard. We do still have set theory. I was wondering, did all of you attend the free course? Is there anyone who did not? I saw it was uploaded and recorded as well. Oh, okay. I think it was uploaded by Athena Studies, right? Yeah, because it was free. Okay. I suggest we leave this recap question to you. Okay, and then you can try it yourself. Yeah, you can share the link in the group chat. That would be great. So is it okay if we skip this recap question? And you can try it yourself because we really don't have time for another one, I'm afraid.
Yeah, I think it is okay, but if we do try it, can we send what we came up with to you, or will we get
Yeah.
the answer to see like if we did it correctly?
Yeah, sure. So I can either send you the answers, or if you prefer, you can. Is that okay, or just to everyone?
Yeah.
Okay, then I will send a photo to you. Yes. So the solution to this one, I will send a picture in the chat. If that's okay with everyone, so you can try it yourself. I think it's good to have one left for you to try. Yes. Yes, exactly. You can go through it and then send individual questions if you have any. So now we have to go through set theory. And we have some exam questions. So do you guys mind if we skip the break, or do you want a 5-minute break after DPLL? Skip the break, yeah, because then we would have more time for the exam questions. So I'm leaving it up to you. Anyone else would rather have a break right now or just go through it? Okay, skip the break. All right, so let's go through set theory. So I believe most of you followed this. Some of you did not, but that's okay. Set theory, I promise you, is way more straightforward than the logic we just did. So let's go through it together. So we have the basic notation of a set. So for the people who did follow it, you can see this. Yeah, so there's a link in the group chat for anyone that wants to follow my entire, it's like an hour and a half, I believe, of set theory. So I probably go through it a bit slower. But as of right now, the people who did watch it, you can see this as like a recap. So you don't really have to revise after this, right? Because then you already did it a couple times. And for the few people that missed it, we're just going to go through it together. It might be a bit faster, but please stop me whenever you like. This is more straightforward than logic, so I believe it will be fine. So the basic notation of a set is as follows. We have this capital letter and we have elements separated by commas inside of the list, basically, inside of the set. Here are some examples of sets. So we could have a set containing numbers, we could have a set containing colors, Honestly, the elements can range from numbers to words to letters to anything. It is just a collection of elements that are usually related. So as you can see, these are related because they're all colors. These are related because they're all letters. And the ones below are related because they're all numbers, okay? So that's important to remember. We have a capital letter, and we have elements separated by commas that are related, okay? So that is a set. So you can have sets of colors and numbers combined if they have something to do with each other. So if you say, I have one pillow that is red and I have 4 pillows that are yellow, then of course you could have it together. But they're usually related. So it doesn't matter in what sense they are related, they just, all right? But anything can be in a set. Yeah, exactly. But usually what you will see is just numbers. So you don't have to think about the relation between them. They're just numbers or letters. So if we have this notation here, what does it mean? We have a set of U where the elements X, where we have elements X, this little line here means basically where. So we have elements X where X is bigger than 20 or smaller than 25. So what do we get in between the brackets? We get any element that is bigger than 20, and we get any element that is smaller than 25. So you might think that this would yield a set containing this, right? But actually, it does not contain this because it has not been specified as well that X are all natural numbers. So that's a bit tricky. So basically, what we do have, we could have something like 20.5 or 23.9 or honestly anything. Does that make sense? So only if this was added, then we would get this set here. Okay. For the people that did not join this one, please just stop me, okay? So now we have the definitions of unordered set and distinct set. So what does this mean? An unordered set is a set that is that stores unique elements in no particular order. And as you can see, these sets are all the same. They're equal to each other, and the order changes. Okay, so a set can be unordered. It doesn't matter as long as you have the unique elements. A distinct set means that you can rewrite the repeated elements such that you have singular distinct elements. The objects of a set have to all be different, and it can be unordered. So that is basically what you have in a set. It can be unordered, and they have to be distinct elements. So these are the two things you need for a set. They can be unordered. Of course, they don't have to be, but they are the same if they are. So ABC is the same as ACB, and they have to be distinct. So you never have any duplicates in a set. All right. Set equality. So a set S is equal to T if they contain exactly the same elements. So what does this mean? Again, we have a little example here. So remember the example from before, right? Now we have 1, 2, 3, 4. And a set T, we have all elements bigger than 0 and smaller than 5. Do you guys think they are equal? Yes or no? No, exactly. And why? Because again, we did not specify that they are natural numbers. So this can include also 0.8, which means it will not be equal to S anymore. Does that make sense? So in our case, they are not equal here. No. And if we add X is equal to N, then they are equal. So that's something to remember. Then we have infinitive sets. So we have 3 examples here. R is an infinitive set. So if we have a set that is just equal to real numbers, Real numbers are like any numbers, right? So that can be anything. We could have the set of capital Z, which is the set of integers, both positive and negative integers. And what are natural numbers? Natural numbers are also integers, but they're only the positive values. So only positive integers are the natural numbers, and both positive and negative integers are the set of integers. Okay. We have something called A minus B. So that's a set of all elements that are in A, but not in B. So if we want to calculate what is A minus B, we can write down both sets. And what do? We check that every time an element is in B, we remove it from A. So could anyone tell me what they think A minus B would yield in our case? So you take A and you remove all elements that are also in B. All elements that are in A but not in B. Yes, great. We indeed would have 0, 4, and 11. And why is that? Because if we check, sorry, my brackets are not great. We check, okay, is 2 in A? Yes, it is. So we remove it. Is 3 in A? Yes, it is. 6 is not. 8 is not. 9 is in A. And that's it. So then we are indeed left with this. Okay, so for the people who didn't attend, is that clear? I think, yes, Jeremy also got it. I believe I scrolled up, you did not attend the one. Okay, great. So then we have Venn diagrams. So Venn diagrams are, in set theory, the colored areas here show what the set represents. So here we have set A, so that is colored as just the set of A. We have all of these other things that we will cover individually, but just know that a Venn diagram basically shows what has been denoted by the set. So if we try a practice question here, it asks which of the following represents the shaded area in the Venn diagram. So tell me in the chat, what do you think? We have this shaded area. So what does it represent in our case? Is it A? Is it B minus A? Is it A minus B? Or is it the complement of B? Okay, I'm seeing D. Great, indeed. So we just saw what A minus B is, right? We take all elements of A, but we remove the ones that are in B, and that's exactly what is happening here. So A has some overlapping elements with B, and it removes them from the Venn diagram. We only color the elements of A, so that is indeed the correct answer, A minus B. All right, so I'll leave this practice question to you, maybe. After you've done everything of set theory, you can come back to this one. So it asks, what do these Venn diagrams represent? And they want you to provide the notation as well as the name. Okay, so I feel like this is a good example question for you to try yourself. So we're just gonna go through it. Then we have something called set membership. So we have this little sign here that says element or not element. So we could say that X is in S or X is an element of S. And similarly here, we say X is not in S or X is not an element of S. So here's a little example. If we would have a set B containing 1 through 5, then 1 is an element of B and 5 is an element of B, right? Because they're right here. But 0 and 6 are not, because they're not in the set. So they are not elements of B. Okay, everything clear so far? Okay. Then we have something called the empty set, which is a unique set that does not contain anything. Okay, So there can never be an object that is in the empty set. And you can write it down either like this, so like kind of like a 0 with a strike through it, or as a literal, just an empty set, nothing inside of the brackets. So here the empty set will continue when we are talking about subsets and supersets. So what is a subset? S is a subset of S if and only, S is a subset of T if and only if for all the elements are in S, but also in T. So what does this mean? S and T share the exact same elements. So that is why when you say T is a subset of S, you can immediately also say S is a subset of T, because it would look something like this. If T contains elements 1, 2, 3, and S contains elements 1, 2, 3, then T is a subset of S, and S is a subset of T. And this is the sign for subset. Okay, here the empty set comes back, so you need to know that an empty set is always a subset for any set. So it doesn't matter which set you have, a subset of it is always the empty set. So empty set is also a subset of S. Empty set is also a subset of T. Okay. Then we talk about a superset. So it's basically the subset sign, but you flip it around such that it becomes this. We say that A is a superset of B when the set A includes B. Okay, so we wanted to include every single element. So if I could write down an example here, I could have the superset of A, which contains 1 through 5. Then B, for example, could contain 2 and 3. That way we can see that set A includes the elements of set B, right? And if you would write this down in a Venn diagram, it would look something like this. This is the set of A, and B is included entirely in A. So then we can say it is a superset of B. Okay, so when it includes the set, it's a superset. When they are equal, so they share the exact same elements, so that will look something like this. Oh, let's try to draw. That would just look something like this. S and T both share the same elements, so it's just one circle in the Venn diagram. Okay, is this clear? That is subset and superset. I'm just going to continue. Yes, okay, great. So the question is here, when is S not a subset of T? Could anyone tell me? If you know now the definition of subsets, when would you say S is not a subset of T? When they are disjoint, exactly. So when they do not share any common elements, right? Exactly. Common elements. Oh God, the writing's getting out of hand. And then a second one could also be like when they do not share. Yes, exactly. When there's an element of S that is not in T. So when they do not share the exact same elements. So if you would have S that is 1, 2, 3, 4, and T that is only 1, 2, 3, then they are not equal, right? So then T is not a subset of S. Exactly. Okay, let's do a little practice question with this one. Yes, they are proper subsets in that case. That's something we will come back to in the next slide. So do we have a subset here? No, exactly. Because we don't have this kind of subset, right? Because then they would have to share the exact same elements. Do we have a superset here? Yes, and what is that? A is a superset of B. Perfect, yes. So it was indeed correct. We don't have a subset of any kind, but we do have a proper subset. So let's check out what that is. In our case here, we would say that B is a proper subset of A. So what does that mean? A proper subset is when S is a proper subset of T if there's at least one element of T that is not in S. Okay? So they do not have to share all the same elements. If they do, it is a regular subset, like we see here, right? There are no elements of T that are different from S. They are the exact same circle. So we have S being a subset of T. And we have a proper subset. Note the notation here. So remember, this was a subset. This is a proper subset. It means that there are elements in T that are not in S. So if you would write down a little example here, we could say that S includes elements 1, 2, 3, and T includes elements 1, 2, 3, 4, 5. Then we say S is a proper subset of T. I got a question before saying, does this then mean that T is a superset of S? Yes, this is indeed the case, because remember what was a superset? It looks like this, right? We have a circle inside of a circle, which is exactly what we have here. So remember that these are kind of interchangeable. If S is a subset, a proper subset of T, then T is a superset of S. But T can be a superset of S even for the first one. For this one, no, because for a superset, it has to include all the elements. And if they are the same, then it's just, the Venn diagram looks like this, right? They're the same circle. So then you cannot say here that S is a superset of T because they share the exact same elements. T is not a subset of S. Yes, exactly. So if your Venn diagram looks like this, that's what you have to look out for. Then it is a superset, and the other way around, it is a proper subset. Okay, so keep that one in mind. This is a proper subset. So let's try a little practice question. Are there any proper subsets in this image? And could you tell me which one that is? Okay, I see A and I see C, but I want a notation where it says blank, blank, blank is a proper subset of blank, right? So what would that be in our case? Remember? Yes, I see. Exactly. So A is a proper subset of B. That is correct. Why? Because they share the same elements, but there are also elements of B that are not in A. So you see the same Venn diagram happening. A is inside of B. Perfect. And then could you say an example, what is not a subset of something? C is not a subset of A, yes, or of B by any chance. Because there's this element outside of all of it, so it cannot be a subset. Okay, let's see if we were correct. Yes. Yes, sorry, proper subset, you're right. Proper. So indeed a proper subset of B, so that's also here. So A is also not a subset of B. Correct. Yes, A is not a subset of B. Because then they would have to share the exact same elements. You can see it here. The elements of A are included in B. C is not a proper subset because the elements of C are, not all of them are included. We only have 2, but we don't have 8. So then it is not a proper subset. Okay. So if someone maybe could tell me this, give me all the possible objects in a set where the elements are a subset of 1, 2, 3. Which elements would I get? 1, 2, and 3. Perfect, exactly. Because what did we say about subsets? They have to be the same elements, right? So if we have a set where it is a subset of 1, 2, 3, then that exact same set will contain elements 1, 2, and 3. Remember here, T was 1, 2, 3, and S was 1, 2, 3, so it's kind of the same. If something is a subset, it contains the same elements. Okay. Then we have cardinality, which means the numbers of elements in a set. So could anyone tell me the cardinality of this first one? 6, perfect. And for the second one? 2. Yes, great. And why is it 2? Because we have 2 elements here. So don't be fooled. These are 2 separate elements because they are separated by the comma here. Exactly. So if this would be an entire set, we would write it like that. And it contains element 1 and element 2. All right. So if there are 25 elements in the universal set and the cardinality of A is 14 and the cardinality of B is 15, and we also have an intersection which is equal to 6, then what is the number of elements in the union? So the union is everything together. So A union B looks like this. And A intersection B is the elements they share. So that would be A intersection B. So could anyone maybe tell me what the answer to this question is? We know that all the elements of A are 14, all the elements of B are 15, and the intersection is 6. So indeed it is 23. And why is it 23? Because we have 14 plus 15. And we remove the intersection, right? If we would not remove the intersection, we would count it twice because it is present in set A, but also in set B. So we have to remove it once, otherwise we're counting them double. So if we want to know what is A union B, we take all the elements of A and all the elements of B, and we subtract its intersection. Okay, still clear so far? Yes, perfect. Okay. So now I have something called the power set, which is the group of all subsets of a given set, and it has n amount of elements. So if we would have a set containing 3 elements, and we know that it has 2 to the n power of subsets, how many subsets would our set have here? Yes, exactly, 2 to the power of 3, which is 8. Perfect. So if you would write down all the subsets, which can also be proper subsets, of course, what do we get? It also tells us it includes the empty sets. Okay, that's the first one. Can anyone tell me any other one? We need 8 in total. 1. So also then 2, 0 and 2, right? What else? 0, 1. 0, 2. 1 and 2, perfect. And the final one? 0, 1, 2, exactly. Because remember, a set is always a subset of itself. So that's perfect. We have 8, 1, 2, 3, 4, 5, 6, 7, 8. Yes. So this would be the power set. Okay. I think this one is clear as well. So we just discussed the union as well. So the union is any element of X or any element of T or both. So just everything combined. So if you would rewrite this, what would its union look like? One, two, three, four, five, exactly. And what is its cardinality then? So how many elements do we have? Yes, 5. And note that we do not count this one double, because if we take its union, it rewrites to that, and we have 5 distinct elements. Okay, perfect. Intersection is kind of the opposite. Remember, we would draw the Venn diagram. You just take whatever overlaps. So we take elements of X and elements of T. So what is the intersection of these two sets here? They're overlapping elements. It's the empty set indeed, because they do not have any overlap, right? ABC does not overlap with 1, 2, 3. So they are disjoint. What is disjointness? Disjointness means that the intersection of A and B is the empty set, as we just saw. So they do not share any common elements. So its Venn diagram would look something like this. So an example would be the set of even numbers and the set of odd numbers, right? Its intersection of even and odd is empty. Okay. So which two sets are disjoint? What do you think? B and C, perfect. Yes, because they do not share any common elements. Remember, we want to find something where its Venn diagram looks something like this. They are completely disjoint. There's nothing in between them, which is indeed the case for B and C. Both B has an intersection with A, C has an intersection with A, but B and C are disjoint. Okay, perfect. Now we have the complement. So what is the complement? The complement of A is the rest, basically. So we take everything except for A. Same for B. The complement of B is everything except for B. Okay? So you can use this little formula if you want to know the complement of A. You take the universal set, which is everything, and you subtract the set of A, such that if you subtract it, you're only left with whatever is not in A. Okay, so you can kind of see this as negation, right? Not A, everything that is not in A. So if you want to find out what the complement is of the union, what would that be? So everything except for the union of B and C. I'm seeing the answer B. Yes, exactly. Because we take B union C, right? And indeed we subtract it from the universe. So we are left with 10, 50, and 65. So then the complement is only this. Yes, exactly. So that was set theory. And now we still have 45 minutes left for the exam question. So that is very nice. Let's see. That was pretty quick, right? Are there any questions about set theory? Anything about the power sets, the supersets, the subsets? I feel like they were pretty clear now. I'm specifically asking the people who did not attend the free course. Is it clear for you? It was clear for me. Great. Okay. I feel like also during the working groups, these were already discussed, right? So it was not completely new. Okay. So let's take a little 5-minute break right now, because we just went through it pretty quickly. So let's take a 5-minute break until 11:50, and then we will have until 12:30 to go through exam questions, right? So I'll give you a lot of time to go through that so that you can prepare. I think it is important to make these together. So I think someone shared the link to the free course. Yes, so that is great. I hope it was all right. Of course, I didn't watch it back. So if you are uncertain about it or you want to watch it at a bit of a slower pace, you can always go back to that. Or if you have a slide where you're like, oh, what was the explanation for this one again? You can refer to the free course link. So thank you for sharing that one. We went through DPLL together, which is great. After this, you will see what exam questions will look like. So I think that is very important. And let's have a little break. I will be right back, and then you can ask me some questions again if you have any. Okay. So we spent some more time on logic and entailment, right? But that's okay because that one was quite tricky for DPLL. And we spent a little while on set theory, and we went through it. Again, if it is not clear, then please refer to the free course recording. So now we have quite some time for exam questions, which is great. So let's just go through it. I thought for exam questions, of course, this is for you, right? The final practice. So I thought it would be nice to give you all maybe, because it's multiple choice, some questions take longer than others. I give you like 1 or 2 minutes per question, and then we go through it, okay? So I think it's easiest if I just give you the question, and what you can do is on the Zoom chat, you can send your answer privately to me so that no one sees your answer, and then I can see what you guys think, and then we can go through it. Is that a nice way of doing it, do you think? All right, yeah. So when you think you know it, just send your message like to me privately on the Zoom chat, and then I can see what you guys think and we can discuss together. That way I can also see like how many of you are done. So that's a nice way of doing it. Okay, so I got 4 answers right now. 5, 6. Give you guys a little more time. Okay. So I'm seeing a lot of answers right now. I see a lot of A. I see some people saying B. And the answer is indeed A. So great job if you got that one. So let's look through it together. It says, let the circles denote the goal states. And you want to find a single solution as quickly as possible. Which algorithm would be the fastest? So what I would do for this question, I would just count the steps that it takes for me to find a goal. So if I apply depth first search, I start at the root. I take 1 step, 2, 3, and 4, and I find my goal. So depth first search takes 4 steps. Then I try breadth first, so we go left to right, remember? 1, 2, 3, 4, 5, 6, 7, 8, before I find my first goal. So breadth first search takes 8 steps. And then of course, depth first iterative deepening, it takes a lot more because you do 1, 1, 2, 3, 1, 2, 3, 4. So that one takes a lot more. So the answer is indeed depth first search. So did the person who answered B also get it right now? Okay, great. So you just count the steps. That's also nice that you only send it to me, that way nobody knows. So don't worry if you make any mistakes. Let's check. Yes, A is the correct answer. So great job. Next question about uninformed search. Depth first iterative deepening always finds the best solution first, such as breadth first search, using far less memory with only a computationally small overhead. So depth first iterative deepening, just like breadth first search, always finds the best solution first, using less memory, but with a computationally small overhead. Okay, I'm seeing kind of a 50-50 split between A and B. Okay, so for anyone that answered true, can you maybe unmute yourself and tell me why you think A?
Hi. Yeah, I thought that the space complexity of the first iterative deepening is only B times D, while the space complexity of breadth first search is B to the power of D. So
Exactly.
that means that the first iterative deepening uses far less memory. I'm not sure about the computationally small overhead parts. But
yeah,
I'm guessing since it doesn't really explore that more nodes, that it's only a small overhead.
Yes, exactly. So indeed, for this, you need to know the table as you refer to. So for iterative deepening, its space complexity is B times L. So times the limit, right? And
no, B times D, I believe.
Sorry, yes, B times D, sorry. And breadth first search is B to the power of D plus 1, right? So this is space. So B is the branching factor. And then for time, iterative deepening has B to the power of D, and breadth first search has B to the power of D plus 1. So as you can see, there's only a small computational overhead.
What does the plus 1 part mean? Because I don't think I've seen that in the table.
Yeah, so it is in both that one and the other one. So for breadth first search, you take depth plus 1. Honestly, you take the branching factor times the depth plus 1 because in breadth first search, when you expand on a node, right, you expand on all of its children. So even if this is the goal and you want to check the goal, you first expand one way down again, right? So I think that's why it's plus 1, because you take the depth and it also checks the generation below it each time. So refer to the table for this one. And honestly, I did not memorize the exact things here, but I just memorized, okay, depth first iterative deepening uses less memory. That is indeed correct. Okay, so let's check it. It is indeed true. All right, so for our next question, it's about uninformed search. The algorithm A does not always find the shortest path to the good solution, as the search is dependent on the quality of the heuristic function. Is that true or false? Seeing some answers coming in. So again, for the last question, I hope that was clear. So breadth-first search uses more memory because when you expand a node, you add all of its children and then keep them in memory. So that's why it takes more. For depth-first iterative deepening, this doesn't happen because it's a depth-first search, so it doesn't expand on all children. It goes down the left first, right? Oh, I wrote down memoir, mean memory. Takes more memory because when it expands on a node, it adds all the children in memory. Okay, so I saw quite a lot of answers for this one. I'm seeing true, 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 false, true, false. Okay, more people have true. And that is indeed the case. So why is that? Can anyone tell me? Maybe Anna? Could you tell me why you chose true?
Yeah, I can. So with the we have A and we have A star, and with the A our heuristic is just the estimate cost. So wherever we kind of end up, it depends purely on how good our heuristic is. And with A star, we use the function that combines the heuristic value and the actual. We use admissible heuristic, so we combine because we've already taken with the heuristic value of how far away are we. So we find the shortest path, and with A star, we don't always do that.
Exactly, that is indeed correct. So it was very important what they just mentioned. So A star, because it uses the admissible heuristic, remember? It is guaranteed to find the shortest path to a good solution. But as this describes, a search does not always find the shortest path because it is dependent on the quality of the heuristic function, right? If it's just an estimation that is based on received information, then it could be that it does not always find the best path. So that is indeed true. So if the question was A star, then it would be false. But because we're talking about a search, it is true. Let's check our answer. Yes, it is true. So I feel like most of you chose true for that one. So that is correct. Okay, so this is quite a big one. So I'll give you guys maybe 5 minutes to solve it. So they want you to consider the following puzzle consisting of 2 white blocks and 2 black tiles and an empty tile, which is this one. The states are coded as follows. So if it's a black tile, we put a B. If it is a white tile, we put W. And if it's empty, we put E. The goal is a configuration where all the white tiles are on the left-hand side of the black tiles and the position of the empty tile is relevant. So any solution could be like that, or like that, or like that, etc. We have some legal actions. So the first legal action is that a tile can be moved to a neighboring position for the cost of 1. And a tile can be moved over a tile to an empty position, so it makes like a little jump, right? For the cost of 2. The related heuristic for the h, basically our h function is the number of white tiles to the right of the black and the number of black tiles to the left of the white. So we want to use A star search, and we want to know which node will be visited after our starting position. So this is our initial node, right? We start with black, black, white, empty, and a black tile, white tile again, sorry. And we have 3 options to go to, which are these 3. And now they want you to calculate the heuristic function, right? And then which one will we choose first? So I'll give you guys some time to go over this. Remember, what is the... Well, I'm not going to give you guys any hints. Never mind. So try this one yourself. So how can we calculate the heuristic value? I'm just going to write down the options, but take a second to calculate them for yourself and tell me which one will A star explore next. Okay, so I got one answer so far. I can tell that person you are indeed correct. Okay, so I have 5 answers so far. Let's wait maybe for a few more. If you don't know, you can also say that. So at least I know I'm not waiting for you to finish. Okay. So now I got quite a few answers. So Noor, could you maybe tell me how you approach this question?
not really sure. It was more of a guess, I guess.
Okay.
I just looked at the other options and it seemed like they will be more costly and this one will cost less. But I didn't actually calculate it or anything.
Okay.
Sorry.
Would you like to try to calculate it?
Um,
So do you remember
okay,
what
sure.
the formula looks like if we have A star? What do we add together?
GN and HN.
Yes, exactly. So in our case here, this is HN, right? And this here is GN. So for this first one, they say a tile can be moved to a neighboring position for the cost of 1, or it can be moved over a tile to an empty position. So what happens in this one?
For this one, only W was moved, so it was a 1.
Yeah, so we have a cost of 1, and then we need to add our cost of H, which is the number of white tiles to the right of all the black tiles, added to the number of black tiles to the left of all the white tiles. So if you would add them up here, which values will we get?
White tiles. Right. Uh, 2 plus 2.
Yes, great, exactly. So that is our value for the first one. We have a cost of 1 for the action and the cost of 2 plus 2 for our H value. So if you would do the same for the second one, what do we get?
It's also 1 plus 2 plus 2.
Yes, perfect. So that's also 5. And for our last one?
Uh, 2 plus 1 plus 1.
Yes, great. So as we can see here, this final one has the least cost, right? So where would A star go to? That one. So you guessed correctly in our case. But for the rest, I think some of you said A as well. So is this clear now why we chose C? Yes, okay, great. So just remember for A star, we have to add things. They're also giving you this, that it has a cost. So that kind of implies that you have to do something with it, right? So we calculate the heuristic value of all the options, and then we see that this one is the smallest one. So then we choose C. Let's see if we're correct. Yeah. All right, let's continue. We have a minimax question. If max plays optimally using the minimax algorithm and it is allowed to start, it will always find a winning strategy. Is this true or false? Okay, seeing you guys are answering this one pretty fast. So I'm seeing quite a lot of A. So Roberto, would you maybe tell me why you chose A?
Sure. So I think it's because if Max is dealt a bad hand, it doesn't matter how optimally he plays, Min will still win.
Exactly. Perfect. So that is the premise of this question. Optimal does not equal winning, right? Because as was just said, if Max has very bad cards, even if it plays optimally, even if it has like the best strategy it can possibly play, if it has bad luck at the beginning because it drew a hand of cards which he just cannot win, it doesn't imply that he will always win. So optimal does not equal winning. And that is why the answer is indeed A. It is false in our case. So that's very important to remember. Optimal does not equal winning. So just like you play yourself in a game, If you have mastered your strategy, but you just have bad luck with like a card distribution or something that relies on chance, then it does not mean you will always win. Okay. I think most of you got that. For the people who chose B, is that clear to you? Yes, great. Okay, perfect. Another one for Minimax. So it says, given a choice between moves A and B in the following tree, which one would Minimax choose, assuming that Max is to move at the root? A or B? Okay. So, Ruvantika, I see you chose B. Could you tell me why? Because Min starts and Min will pick 50 and 51. Yes, that is correct. And we've been given the information that Max is at the root. So which one would Max choose? B, because that is the biggest value, 51. So B is indeed the correct one. Max will choose the value of B that way. Yes. So let's check. B is indeed the correct answer. I think most of you got this one. Is it clear for the rest as well? So this is kind of tricky that it says Max is to move at the root. So it is not the first one in the go. Yeah. So we have Min and then we have Max. And that is why. Okay, great. Just checking for the rest. So B is indeed the correct answer. Before we move on, I just wanted to make you guys aware that there's an evaluation form, which is really helpful for Athena studies and also for me. So if you could just take a minute to scan the code, and then we will continue with our exam questions, and then after the session you can fill it in. But just scan the code for now, because this is really important. So I hope you guys are learning a lot, of course, but let me know via the evaluation form. You also received it in your email probably, but I just wanted to make you guys aware of this. So I'll give you a few seconds to scan it, and then we can continue with the exam practice. Okay, so I hope you scanned it. If not, I'm going to show it at the end of the presentation as well again. So let's do another Minimax question. So this one is about alpha-beta pruning. And they say if you apply the Minimax algorithm with alpha-beta pruning, which nodes can you prune? More than one answer can be correct. So this one might take a little while. Let's give you guys 5 minutes. So until 12:25. And then we can discuss it together. Okay, so 2 more minutes. I think 3 people answered by now. Okay, so I'm seeing a lot of people saying 3 and some also saying 5. So let's go through together. So we check for this first one, min will choose 4, right? So what do we know for max? We have at least 4. Okay, I don't know why. Okay. So then our question is, do we check the rest? In our case, we do have to check this one, because imagine if it is bigger than 4, then max will have another outcome, right? So we check this first node. We know we have at least 0 or smaller in this case, because it's min. I don't know why I cannot draw the infinity sign. Okay, so we know we have at least 0 or less. So 3 is indeed correct. We can prune h, because if this is a higher value, then min will not choose it because we already have 0. And if it is a lower value, we know that max already has 4. So it will also not choose it if it was smaller, right? So we can indeed prune h here. So then can we check D? Yes, we have to check D, because if this has a bigger outcome, then it changes the outcome for max. So let's check. We have something smaller than 3 or 3, right? Because it's min's turn here. So do we check J? No, indeed, we can also prune it. And why is that? Because if it was bigger than 3, then min would not choose it here. And if it is smaller than 3, which means it could be something like 2, max will not choose it. So 3 is indeed the correct answer. But it also says more than one answer could be correct. I see some people also chose 5, which is indeed correct. So let's check why. So here we only have one node, so we know that min will choose 5. We also know now at the top that max will choose 4, so we have 4 or something smaller. That is our interval up here. Okay, so if we check this branch, let's say max now has 5 or something bigger. So let's say this was 7. Max could choose it here, but min is at turn at the top, so it will not choose it if this was 7. So that will not change the outcome of the game. And let's say this was smaller, so 4, then max would not choose it. So does this entire subtree matter for the outcome of the game? No. So we can prune all of these. So indeed, 3 and 5 is the correct answer. So I saw a lot of people saying 3, but remember, you can also prune this entire subtree, because max already has 5 or higher. So even if it chose 7, it will not be chosen at the top. And if it would be lower, then it would not be chosen here. So nothing changes. Is that clear for everyone? I see a lot of you chose 3. Only 2 people also had 5. So does that make sense why we include 5 as well? We prune N, P, and Q. I take silence as a yes. Okay. Yes, okay, great, thanks. So indeed 3 and 5. We have some questions on set theory. Let's discuss this one. So true or false, if A and B are disjoint, then A union B is the empty set. lot of you already answered. And you're all saying B. That is indeed correct. If they are disjoint, meaning they do not overlap, their union is still just everything inside of this. So disjointness does not affect the union. It will just still be all the elements of A and all the elements of B. What is the empty set here, though, is the intersection, right? Because they are disjoint, so they do not have any overlapping elements. But let's check. Yes, indeed, if they are disjoint, then the union is empty. That is false. That does not happen. Okay, so another exercise on set theory, which kind of looks similar to the one we had before. What do you guys think about this one? So the complement of the union of A and B. Okay, yes, I'm seeing a lot of people saying B. That is indeed correct, because we take A union B, and then we take the complement. Remember, that is everything but. So we take all of these values here. Let's check. Yeah, that is indeed the case. Okay, so unfortunately, I see now it is 12:30. What is nice, though, is that in these slides, I have a lot more practice exam questions for you to go through. So I have one about logic, 2 about DPLL, which you can solve yourself. And then here I even have extra practice questions, so like a lot of them. So you can do those on your own time and ask me questions in the group chat, of course. So unfortunately, we don't have enough time to go through them together, but I believe this is good, like separate practice for you. And that way you can yes. So I hope you guys enjoyed that. And I want to thank you all very much for your participation. I hope it was very helpful. And good luck with your exam, of course. Here's the evaluation form again if you haven't scanned it yet. And then again, I'm there in the group chat, so you can make any practice exam questions, go through these slides, go through extra theory, go to the working groups, the slides, anything, and you can ask me questions there. So just note that from 1:30 to 4:30, I also am teaching another group. So if you send any questions then, I might not see it yet. But definitely leading up to Wednesday, I will make sure I check your questions. And of course, if there are fellow students in the WhatsApp group that think they know the answer, you can help each other out. I personally always found that if I'm studying for an exam and I help other people with their questions, that makes me think like, oh, wait, so I know it. So that is also a good practice for yourself. And then I'll be there to say whether it is correct or not. So don't worry about that. Then if you scan the evaluation form, I'm going to say goodbye. You can leave the Zoom session. And then I will see you all maybe tomorrow. If you signed up for one of my extra working groups that I'm teaching as a TA. And otherwise, maybe I am your TA for the normal working group. So then I'll see you there again. Yes, thank you very much. I hope it was helpful. And then I'll see you guys later. Bye, everyone. Bye.